Hello everyone, so in this video we're going to solve the January 2021 Physics IAL Unit 2. Now I obviously cannot show the paper in the screen, the official paper of Pearson Edexcel in the screen. So I'm just going to give you the solution, explain you the questions, and I hope it will be useful. So let's start. I'm solving the question number 1 of section A. Question number 1 of section A. Question number 1 is the unit of power is the watt. Which of the following is included in the SI base units for power? A. Newton, B. Kilogram, C. Joule, D. Ampere. So we need to choose out of the 4 options that which of these are actually included in the base unit for power. Now it is already said in the equation that the unit for power is watt. Watt is the unit for power, and we know that watt is not a base unit, it's more like a derived unit, and we need to break it down into its simpler forms. So watt is broken down into joules per second. Now second is again a base unit, but joule is not, so we need to break down the joule into its base units, that is Newton meter by second, and meter second, these two are base units, but Newton is not, so we need to break down Newton into its simplest form, and that would be kg meters per second square into meter divided by second. And we can see that kg is actually is a part of the SI base unit for power. That means that option B, kilogram, is the correct answer for question number 1. I hope question number 1 was clear. I'm moving to question number 2. Question number 2 has a drawing, and I've already did the drawing before, so I'm just moving to that page. Here is the drawing for question number 2. So this is question 2. I'm solving the question 2 from section A. The question 2 says, the diagram shows a combination of 3 resistors of resistance X, Y, and Z. Which of the following gives the total resistance of the combination? So we need to find an equation that would give the total resistance for this combination. We can see here that there are 3 resistors connected in both parallel and series. The resistors that are connected in are connected in series are X and these two. Let me consider these two as a group, the both Y and Z. Let me consider both Y and Z as a group, and I'm gonna name it as R subscript T. So X and RT are connected in series. Let me write it down at the side. X and R subscript T are connected in series circuit, and the RT, that is the Y and Z, are connected in parallel circuits. So Y and Z are connected in parallel circuits. Now there are going to be different calculations to find out the total resistance for the parallel and series circuits. So let us start with the series circuit. In order to find the total resistance in series circuit, you just need to add up the different resistances. That is, total resistance would be X plus R subscript T. Now R subscript T is consisted of 2 different resistors connected in parallel. So now we need to do the parallel circuit calculation to find the value for RT. So value for R subscript T is basically the reciprocal. We need to add the reciprocal of the different resistors together to find the total resistance in parallel circuit. We need to add the reciprocal of the different resistors to find the total resistance of parallel circuits. So here an equation for this would look like 1 over RT is equals to 1 over Y plus 1 over Z. Now we need to make just RT the subject of this equation, and for this we need to do the LCM for Y and Z, and that would be Y plus Z over YZ, and then cross multiplication would look like RTY plus Z is equals to YZ, and if you just make RT the subject, and that would be YZ over Y plus Z. and therefore we can just put this, the value for RT, into the equation for total resistance, and it will look like total resistance is equals to X plus YZ over Y plus Z, and this is exactly option C. So option C is the correct answer for question number 2, X plus YZ over Y plus Z, and this is the correct answer for question number 2 with all the working shown in here. I hope question number 2 was clear. I'm moving to question number 3. Question number 3 doesn't have any drawing, so let me move to my blank pages. Now I am gonna solve question number 3 from section A. Question 3 from section A. So question 3 is, ultrasound can be used to investigate organs inside the human body. Which of the following statements about ultrasound is correct? So here in question number 3, 4 sentences are given that, and they are claiming that this sentences, one of these sentences has the correct statement about the a property for ultrasound. So we need to just identify the sentence which has the correct property for ultrasound. So let's start. Option A says all of the reflection, all of the ultrasound is reflected at a boundary between different tissues. Now, not all of the reflection occurs between the boundary change of different tissues. I agree, some reflections do take place in the boundary between different tissues, but not all of the reflection. Okay, so option A is wrong. The most the most reflection that actually occurs when the ultrasound is moving from air boundary to the body, to inside the body, and that's why we apply gel onto on the surface of the skin to prevent reflection, right? So option A is not the correct answer. Option B says ultrasound travels faster in air than inside the body. Now this is a kind of true statement because air is less dense than body, and obviously any medium that is less dense, the waves will travel faster in that specific less dense medium. So obviously ultrasound travels faster in air than it travels inside the body. This is not a specific property for ultrasound. This is more like a property for the generalized waves. So option B is also not correct. Option C says ultrasound with a greater wavelength gives an image with a higher resolution. Now, greater wavelength doesn't ever give higher resolution. It's always the opposite. A smaller wavelength, let me rub it out, and I'm explaining the C option. A smaller wavelength always gives an image with higher resolution. High resolution, which means that if the ultrasound has a greater wavelength, it would certainly give an image with a lower resolution. So option C is also not correct. Moving to option D. Option D says ultrasound with a shorter pulse duration gives an image with a higher resolution. Shorter pulse duration. Pulse duration is basically it basically means that time period. So let me write it down. Shorter pulse duration basically means small time period. Now we have this equation that connects time period with frequency, and that is T is equals to 1 over F. And according to this equation, we can see that time period is inversely proportional to the frequency for a wave, which means that any wave which has a smaller time period will certainly have a high frequency. So from this we can say a small time period produces a high frequency. A high frequency. So any wave that has small time period produces a high frequency. And according to another equation, that is wave speed is equals to lambda into frequency. Now if we rearrange it and make wavelength the subject, it will be like velocity over frequency, and here we can see that wavelength is inversely proportional to frequency. And as wavelength is inversely proportional to frequency, a high frequency wave will have a small wavelength. So according to this equation, lambda is equals to V over F. We can say that a high frequency wave will have small wavelength. And as I've already said this in option C, that a smaller wavelength, a wave with a smaller wavelength always produces an image with a higher resolution, which means that this sentence is actually leading to that term, that is, a smaller wavelength produces an image with higher resolution, and a smaller wavelength is actually related to small time period. We have already did the calculations, like from a small time period, according to the equation T is equals to 1 over F, as time period and frequency are inversely proportional. So a wave which has a smaller time period will have a high frequency, and according to the equation lambda is equals to V over F, we can see that a wave with a high frequency will certainly produce a small wavelength, and a smaller wavelength will have an image with high resolution. So smaller wavelength produces an image with higher resolution, and in that case option D is the correct answer. So option D is the correct answer for question number 3. Small time gives higher resolution. So option D is the correct answer for question number 3. I hope question number 3 was clear. I'm moving to question number 4. Let me move to another blank page. Now I am solving question number 4 of section A. Question number 4 of section A says, electromagnetic radiation can be described in terms of a photon model. Which of the following demonstrates the photon model of light? A. Diffraction patterns. B. Huygens construction. C. Photoelectric effect. D. Plane polarization. So we know that light is a thing that actually behaves like both wave and particle. It has both the nature of a wave and particle, and there are certain laws and certain theories based on the two different models of light. Now option A says that if diffraction pattern actually demonstrates the photon model of light or not. Now we know that diffraction patterns demonstrates the wave property of anything. Like we have already memorize this from our IGCSEs, that waves can be diffracted, refracted, or reflected, right? So diffraction is a property of wave and not a property of photon model. So option A is not the correct answer, because diffraction patterns shows the wave property of light. So option A is not the correct answer. Option B says Huygens construction. Huygens construction basically says that every source on a wave, so every point on a wave acts as a new source for a new wave. So again, this is a wave property, not a photon model for a light. Option C is the correct answer, because it says that photoelectric effect. Now photoelectric effect is actually the photon model for a property, because in photoelectric effect the photon provides enough energy for the electrons so that they can escape from the metal surface. The photons provide enough energy to the electrons so that the electrons can escape the metal surface. So that case, for question number 4, C is the correct answer, because photon provides enough energy I made a mistake, sorry. Energy for electrons to escape metal surfaces. So yep, question number 4, the answer for question number 4 is option C. I hope question number 4 was clear. Moving to question number 5. Now question number 5 and 6 both have a common diagram, and I have already did the diagram before, so I'm just moving to that page. Page number 2 has the diagram for question number 5 and 6. This is the diagram provided in your question paper for question number 5 and question number 6 of section A. Now question number 5 is, the diagram shows the circuit used to determine the internal resistance small r and EMF of a cell. Question number 5 says corresponding values of potential difference and current were taken after adjusting the variable resistor. A graph of voltage on the y-axis against current on the x-axis was plotted. Which of the following is correct? So here question number 5 says that using this circuit they have altered the value for variable resistor, and for the altered variable resistor's value, the value for voltage and value for current was calculated, and then they plotted a graph of voltage against current. Now which of the four options, the four options have different sentences about the graph of V against I, and they want you to answer that which of the four sentences have the correct answer that you can use it from the graph. So let us first draw the graph for voltage against current. Now before that, let me show you that this small r is actually the internal resistance of the cell. So this small r represents the internal resistance. And this is a variable resistor. As it is a variable resistor, that means it also has some of its own resistances, right? So the value for this resistance would be capital letter R, and capital letter R indicates the resistance of variable resistor. So it indicates the resistance of variable resistor. So now let us first draw the graph for V against I. Usually the graph for V against I has a one fixed shape, that is V on the y-axis, I on the x-axis, and the graph actually looks like this. This is supposed to be a straight line. Now my one doesn't look like a straight line actually. Let me draw it again. Okay, better than the before, so it will work. This is a straight line sloping downwards, and when the graph crosses the y-axis, this is the value for EMF. Now as we can see that the internal resistance and the variable resistor are actually connected by using one wire, which means that R and small letter r, internal resistance, and the variable resistance are actually connected in series circuits. And we know that in series circuits they both share the same current. Like all of the components that are connected in series circuits all will have the same current. Current is constant for every component, but it is the voltage that gets divided in series circuit. So here the voltage gets divided, and now we can the total EMF will be divided into internal resistance and the variable resistor. So the value for total EMF, we can write it as voltage of the internal resistance, voltage subscript R, plus voltage subscript variable resistor. So this is an equation indicating the total EMF for this circuit, and that's how they gets divided between the internal resistance and the variable resistor. Now as we know that according to the equation V is equals to I R, we can use it for the internal resistance. Now it will be like EMF is equals to, now we are not going to write V subscript R, we are going to write RI. Like we are just removing the V with its value, that is resistance plus current, that's RI plus V subscript R. V subscript R indicates the voltage of the variable resistor. So now if you make V subscript R the subject of the equation, it will somewhat look like negative R into I plus EMF. Now this is exactly in the form of Y is equals to mx plus C. Now here Y is the voltage of the variable resistor, M is the gradient and it is the value for negative internal resistance, X is current, so current is X, and C is the EMF. Now this was the working that I did for question number 5. Now let's move to the options and see which one is the correct answer for question number 5. Option A says the area underneath the graph is the total energy dissipated by the cell. So it is wrong. Let me show you why option A is wrong, because it says that total energy dissipated in the cell is actually shown in the area under the graph. Now the area for this graph is actually a triangle, and the area for the triangle, the formula for the area of this triangle would be half into current into voltage. Now current into voltage is just power and not the energy. We need to multiply time with it to give a value for the total energy dissipated. So that's why option A is not the correct answer. Option B says the gradient of the graph is R, which is wrong because the sentence misses one point, that is the negative gradient of the graph is R, because here you see m is equals to negative R. That means the gradient has to be negative to give it a value for R. Option C says the graph shows that V and I are directly proportional. Now this is not a graph where it shows that the two quantities are directly proportional. If the two quantities were actually directly proportional, the graph would have been look like this. The graph would have a shape of y is equals to x shape, and this is not a y is equals to x shape, and that's why we can say that option C is not the correct answer, because the graph doesn't show that voltage and current are directly proportional. So option C is also not the correct answer. Option D says the y-intercept of the graph is the EMF, which is correct, because here you can see that EMF is equals to C, and C is the y-intercept. The value for y-intercept is C. So option D is the correct answer for question number 5. So this is the correct answer for question number 5. I hope question number 5 was clear. I'm moving to question number 6. The resistance of the variable resistor is R. Which of the following gives the current in the cell? So here it says that the variable resistance is R. We have already said this at the top, that I considered capital letter R to be the resistance of the variable resistor. So whatever. In question number 6, it says which of the following gives the current in this cell. So now we need to find out the current in this cell. Again, I'm going to use the equation EMF is equals to the voltage of the internal resistance and the voltage of the variable resistance. That is this equation. EMF is equals to V subscript small r plus V subscript capital letter R. So if I use this, I actually doesn't have any space, so I'm moving to another page for question number 6. I'm solving question number 6 of section A. Question 6 section A. Now question 6 section A wants you to find the value for the internal current, value for the formula that gives the value for the current in this cell. Now we have already seen in the diagram that the internal resistance and the variable resistor are actually connected in series, and in series circuits the voltage gets divided. So that's why we made up an equation that was EMF is equals to sum of the voltages, that is some voltage for internal resistor and voltage of variable resistor. Now we know that equation V is equals to IR. This is an equation for voltage, and we can use the value for IR instead of the value for V. So we can write it as EMF is equals to internal resistance current plus variable resistance current. And the I is present in both of this, so we can make I the common, we can take common I, and that would be look like R plus internal resistance, and if you make I the subject, it will be EMF over R plus small r, and this is exactly option C for question number 6. So option C is the correct answer. Option C, the formula provided in option C will give you a value for the current in the cell. So option C is the correct answer. EMF is equals to R plus internal resistance. And this was the working for question number 6. I hope question number 6 was clear. Moving to question number 7. Question number 7 also has a diagram, so I'm just moving to that page. Question number 7 has a graph. Question 7 of section A. Here question number 7 says a graph of displacement against time for a point on a transverse progressive wave is shown. Which of the following statements is correct? Statement 1 says that the amplitude of the wave is 20 centimeters. Now amplitude is not the 20 centimeters. Amplitude is basically the maximum height from its equilibrium position. And it says that this is the value for 10 centimeters. So amplitude for this wave shown in this graph is 10 centimeter, not 20 centimeters. So option A is not correct. So here let me write it down. Amplitude is equals to 10 centimeter. So option A is not correct. I'm skipping option B and moving to option C because option C says the period of the wave is 0.2 seconds. 0.2 seconds is basically the height value for the half time period, because time periods are always calculated from throw to throw or crest to crest, like this point to this point, or from this point to this point, or you can take the value from like this point. No, yeah, these are the four like points from which you can actually take the value for time periods. So time periods for both the things is that from crest to crest we can see that it's 0.4. So let me write it down. Crest to crest, the time period for this wave from crest to crest is 0.4 minus 0, which obviously gives a value of 0.4 seconds, and time period from throw to throw is 0.6 and 0.2. So 0.6 minus 0.2, which gives a value of 0.4 seconds again. So the value for the time period shown in this graph is 0.4 seconds and not 0.2 seconds. So option C is also not the correct answer for question number 7. Option D says the wavelength of the wave is 0.4 meter. Now I actually don't know. I mean, the graph that is provided for question number 7 doesn't provide any information for wavelength, because in order to find the wavelength for a wave from a graph, the graph has to be of displacement against distance. The graph has to be of displacement against distance. So a graph of displacement against distance is required to find the wavelength for this wave. A displacement against time doesn't ever provide you the value for wavelength, and this is exactly what the graph is showing. Displacement against time. This kind of graphs will give you a value for frequency, amplitude, time period, but not for wavelength. So that's why we cannot say if the wave for this wavelength for this graph is actually if the wavelength for this graph is actually 0.4 or not, because it's not provided in the graph. So that's why option C, D or A is not the correct answer. The last option is B, and that is the correct answer. Let me explain it to you why. Option B is the correct answer. B says that the frequency of the wave is 2.5 Hertz, and we have already calculated the time period for this wave, and that was 0.4 seconds. According to the equation, F equals to 1 over time period, it becomes 1 over 0.4, and if you calculate 1 over 0.4, you get a value of 2.5 seconds. So B is the correct answer because it gives you the correct information from this graph. So B is the correct answer for question number 7, 2.5 Hertz. Sorry, I made a mistake. It's supposed to be Hertz, HZ. So B is the correct answer for question number 7. I hope question number 7 was clear. I'm moving to another blank page to solve question number 8. Question number 8 of section A. Question 8, section A says a ray of light travels through glass towards a boundary between glass and air, the critical angle for this boundary is 42 degree. Which row of the table is correct? Here the diagram would look like something like this. This is the glass and this is the air, and the light is actually traveling from glass and striking the glass air barrier with an angle of incidence that changes for a certain period. This is the light striking the ray, so light striking the boundary, and in option A for question number 8 says the angle of incidence is 40 degree. Angle of incidence is 40 degree, and it was already provided that the critical angle for this boundary glass to air was 42 degree. So value for critical angle was 42 degree. As we can see that for when the angle of incidence is 40 degree is less than 42 degree. 40 degree is less than 42 degree. That means both refraction and weak reflection will occur, because incident angle is less than critical angle, and that's when refraction and weak reflection occur. So here both refraction and weak reflection will occur. Weak reflection will occur, and therefore the diagram would actually look like some rays escaping from the glass medium, that is the refracted ray, and some rays will actually be reflected, like very weak rays will be reflected. So this is the graph, so this is the diagram. That's how it would look like if the angle of incidence was 40 degree. So here option A and option B both says that if the angle of incidence were 40 degree, all of the light is refracted. Now at an angle of 40 degree, when the angle of incidence is 40 degree, all of the light is not reflected and all of the light is not refracted. Both reflection and refraction occur, but not any one of these occurs at 40 degree incidence angle. So that means option A and B are incorrect. Now moving to option C. Option C says that the angle of incidence is 45 degree, and when the angle of incidence is 45 degree, all the light is refracted. Now let me draw another diagram for the option C. Option C says the, let me just change my ink color. Option C says the glass, this is the glass boundary and this is the air boundary, and the light was originally moving from this part, and the angle of incidence for this part forms is 45 degree. And now we can see that 45 degree is greater than this critical angle. 45 degree is greater than 42 degree, which means this cover up the one of the laws for total internal reflection. So as one of the laws for total internal reflection is covered, that means no refraction will occur in this situation. All the light will be reflected, and that means option D is the correct answer, because it says at the angle when the angle of incidence is 45 degree, all the light is reflected, and all the light is reflected means total internal reflection is occurring. So that means here the wave will be traveling from something like this, in this direction, backward towards the glass, and there will be no refraction, only total internal reflection will occur. And in that way option D is the correct answer for question number 8. So option D is the correct answer for question number 8. When the angle of incidence is 45 degree, that is greater than the critical angle, all the light is reflected, that is total internal reflection occurs when the angle of incidence is greater than the critical angle. I hope question number 8 was clear. Let me zoom out so that you can diagram or match the both diagrams. And question number 8 is clear, so I am moving to question number 9. Question number 9 of section A, question 9, section A. Question 9 says in 1924, de Broglie suggested that electrons have wave properties. The de Broglie equation states lambda is equals to Planck constant over momentum. So here the equation is lambda is equals to Planck constant over momentum, and which of the following is correct? There are 4 statements and we need to choose which one is correct for the de Broglie equation. So option A says the de Broglie wavelength is independent of the mass of the particle. Now it is completely wrong, because the denominator, the momentum in the denominator actually contains the mass of the particle. And if you like to break it down, I'm breaking it down for option A. Lambda is equals to height over momentum, and momentum can be broken down into mass into velocity, and here this is the value for mass. And from this equation we can say that mass is inversely proportional to the de Broglie wavelength. Wavelength is inversely proportional to mass. So yes, the de Broglie wavelength is dependent of the mass of the particle. So it depends on the mass of the particle, and that's why option A is not the correct answer. Option B says that the de Broglie equation can be used to calculate the momentum of a photon, which is correct, because if you rearrange the original equation and make P the momentum of the subject, it will be Planck's constant over wavelength, and then you can find the momentum of a photon. So that's why option B is the correct answer. Option C, on the other hand, let me explain option C still, because they are also provided in the question. So option C says the term P represents the mass of an electron multiplied the speed of the light. No, it's wrong, because the term P represents, the term P here, it represents the mass of the electrons and the speed of the electron, not the speed of the light. It represents the speed of the electron and not the speed of the light. And option D says the value for h depends on the particle involved, which is again wrong, because the value for h is constant. That is, h is equals to 6.63 into 10 to the power negative 34, and this is always the same value. The value for Planck's constant is always the same value, and that's why option D is also not the correct answer. So the only correct answer for question number 9 is option B, and that is we can calculate the momentum of a photon using the de Broglie equation. So option B is the correct answer for question number 9. And if it's clear, so we are moving to question number 10. Question number 10 says in a series circuit 3.1 into 10 to the power 19 electrons pass a particular point in a time of 30 seconds. Which of the following gives a magnitude of the current in amperes in this circuit? So here question number 10 has a certain number of electrons passing a point within 30 seconds. So question number 10 in section A, at first we need to find the total charge for this huge number of electrons. We know that one electron has a charge of 1.6 into 10 to the power negative 19. In that case, if we are dealing with 3.1 into 10 to the power 19 electrons, the total charge would be 3.1 into 10 to the power 19 into 1.6 into 10 to the power negative 19. And this is the value for the total charge that is passing through the circuit. And now according to the equation, Q is equals to IT. If you make I the subject, it will be Q over T. The value for Q for this circuit is 3.1 into 10 to the power 19 into 1.6 into 10 to the power negative 19, and divided by the time. The time for this equation was 30 seconds. So it's divided by 30. And you can see that this is exactly the option for option A. This is exactly the part A for this question number 10. So option A is the correct answer for question number 10. Now with this, our section A ends. I'm moving to section B. So now I'm gonna solve question number 11 from section B. So question 11 from section B. So question number 11 says a copper wire of radius 0.4 millimeter carries a current of 5.1 ammeter. ampere. Calculate the drift velocity of the electrons in the wire. Number of charge carriers per meter cube of the copper is 8.5 into 10 to the power 28. So the different informations given in the questions are, we need to collect it. So here the radius, the value for radius is given. The value for radius is given in millimeters, and that is 0.40 millimeter. And now we know that we have to use this value for we need to use value to calculate the value for the area, but we need to find the area in meters. So for that we need to convert the value of radius from millimeter to meter, and that would be, we have to multiply 10 to the power negative 3, and that would make this value as 4 into 10 to the power negative 4 meters. So the radius is now 4 into 10 to the power negative 4 meters. And now we have to calculate the area. The area is pi r square, pi 4 into 10 to the power negative 4 square, and this is the value. This gives a value of 5.0 into 10 to the power negative 7 meters square. So this is the value for the area. Now you have to find the value for drift velocity. So in an equation connecting the drift velocity was I is equals to NAVE, and we have to make V the subject because V represents drift velocity, and that would be I over NAE. NAE. N is the number of charge carrier, I is current, A is area, E is the charge of an electron. So let's put in the values together. Here the value for I was 5.1. So 5.1 would be on the numerator, and on the denominator the value for N was 8.5 into 10 to the power negative 10 to the power 28. So value for N is 8.5 10 to the power 28. And then we need to find multiply the value for area. We calculate the value for area here, and that was 5.0 into 10 to the power negative 7. And then we need to multiply it with the value for charge of an electron. The charge of an electron is a constant, that is 1.6 into 10 to the power negative 19. And if you calculate all this, you get a value of 7.4 into 10 to the power negative 4. 7.5 into 10 to the power negative 4 meters per second. And this is the value for question number 11. This is not visible in the screen, so I will just shift it in here. 7.5 10 to the power negative 4 meters per second. And this is the value for question number 11. I hope question number 11 was clear, the entire working was clear. Now I'm moving to question number 12. Now question number 12 has a drawing, so I have to move to a certain page because the drawing is already done. So this is the drawing for question number 12. Question number 12 says, a student investigate the superposition of water waves in a ripple tank. There are two sources of waves. Source 1 is represented as S1 and source 2 is represented as S2, which are in phase. The diagram shows the position of successive crests of each wave at an instant in time. Explain the type of superposition taking place in position A and at position B on the diagram. So we need to say that if at position A or at position B, if the waves are meeting constructively or destructively. So here first look at for position A. Position A from source, we need to find the wavelength of position A from source 2 and source 1. We need to find the wavelength of position A for from both the sources. So here we are doing the work for position A. So here position A is on this part, and if we count the number of wavelengths away for S2, it will be 1 wavelength, 2 wavelength, 3 wavelength, 4 wavelength, and it's almost the position is almost between its 4 and 5, so it's considered as 4 wavelength, 4.5 wavelength. So source position A is 4.5 wavelength from source 2. So let us consider as Source 2 gives a value for 4.5 wavelength, 4.5 lambda, and for position, for source 2, this is 1 wavelength, 2 wavelength, 3, and that's 3.5. So for source 2, the wavelength is 3.5 lambda. Now we need to find the path difference. We can find the path difference by subtracting the two sources, and that would be 4.5 lambda minus 3.5 lambda, and this gives a value of 1 lambda. And as the coefficient for lambda is a whole integer number, so it means that the two waves superpose constructively at position A. So let me write the explanation in words. At position A, the waves superpose constructively because their path difference is whole number of lambda, because their path difference is whole number of lambda. And this was the explanation for position A. Now we have to do the exact explanations for position B. So I'm going to use different inks for position B. Position B is, let us first find the wavelength of position B from source 2. This is 1 wavelength, 2, 3, 4, and exactly at 5 wavelength. Position B is 5 wavelengths from source 2, and we have to do this for source 1. So 1, 2, 3, 3.5. So position B is 3.5 wavelength from source 1. So let us write these informations for position 2. Position B, Position B from S2 is 5 wavelength, and from S1 is 3.5 wavelength. Now we can have calculate the path difference. Path difference would be 5 lambda minus 3.5 lambda, and that is 1.5 lambda. And as it is a odd number of lambda, odd number of wavelength, this indicates that the waves superpose destructively at position B. So here we need to write an explanation. At position B, the waves superpose destructively because their path difference is odd number of lambda. Odd number of lambda. And with this, our question number 12 ends. Let me zoom out so you can clearly see the entire working. And this was the end for question number 12. I hope question number 12 was clear. Let me zoom in. So this is for part position A, and this is for position B. Now I'm moving to question number 13. Question number 13 has a drawing too, and this is a drawing for question number 13. Question 13 of section B. Question 13 says a student investigate how light intensity affects the resistance of a light independent resistor. She set up a circuit using a cell with negligible internal resistance as shown. The EMF of the cell was 1.5 volt when the lights in the laboratory were switched off. The voltmeter reading was 1.19 volt. Calculate the resistance of the LDR when the lights were off. So we need to find the resistance of the LDR when the lights were off. Now, in the second line of the question, it is stated that when the lights in the laboratory were switched off, the voltmeter reading was 1.19 volt. This 1.19 volt is the voltage for the fixed resistor, because here in the circuit, two things are connected in series. That is this resistor and the LDR. Now, when the switches or when the light was switched off, the voltmeter is connected to the resistor, and here in the question it says the voltmeter reading was 1.19 volt, indicating when the lights were off, the voltage for this resistor was 1.19 volt, and the value for its resistance is also given, that is 5 kilo ohms. So you can find the current inside the resistor when the lights were switched off. So first we need to state it that voltage of the resistor when the lights were switched off was 1.19 volt, and according to the equation V is equals to IR, the value for resistance for this resistor is also given. We can calculate the I by rearranging the equation as V over R. The value for V was 1.19 over 5,000, 5 into 10 to the power 3, and if you calculate it, it gives a value of 2.38 into 10 to the power negative 4 ampere. This is the value for the current inside the resistor when the switch was off. Now, as the two components are connected in series circuit, the current is same for every component. That means that current inside the LDR when the switch were off was also 2.38 into 10 to the power negative 4 ampere. So when switch was off, I inside the LDR is 22.38 into 10 to the power negative 4 ampere. And as we have the value for the current, and we also knew that the total EMF of the entire circuit was 1.50 volt, and as the voltage actually gets shared in the series circuit between the different components, so here we can find it as EMF is equals to V of the resistor plus V of the LDR. And if you make the V of the LDR the subject, that would be V of the LDR the subject, and that would be EMF minus the voltage of the resistor, EMF minus VR, and that is the the value for EMF was 1.5 minus 1.19. This was the value for the voltage of the resistor, and if you subtract it, you get a value of 0.31 volt. So this is the value for the voltage of the LDR, 0.31 volt. And again, using the equation V is equals to IR, we have to make R the subject. This is the we are now calculating the value of the resistance of the LDR, so we can write it as LDR, and that would be 0.31 voltage over current, 2.38 into 10 to the power negative 4, and if you calculate it, you get a value of 1303 ohms, which you can write it as 1300 ohms. And this is the answer for question number 13A. This was the answer for question number 13A. I hope question number 13A is clear. This was the answer for question 13A. Question 13A is done. Now I'm moving to question 13B. In question 13B, it says that when the lights were switched back on, the student discovered that it was impossible to calculate the resistance of the LDR using this circuit. The student said that with the lights on, the resistance of the LDR was about 9 ohm. Explain why the student was unable to use the circuit to determine the resistance of the LDR when the lights were on. The resolution of the voltmeter was 0.01 volt. So here the problem arrives here is that when the lights were on, the LDR was not receiving light from one source. It was receiving lights from different sources, and then as light increases, the resistance decreases a lot. And as V is equals to IR, resistance and voltage are directly proportional. So as resistance decreases, voltage also decreases. Now, when the lights were on, the voltage of the voltmeter decreases is very less. Like the voltage of the voltmeter would be very less than the resolution of the voltmeter, and that's why it would be harder for her to determine the value of the resistance. Let me explain it in the math form. I am now solving 13b. Let me move to a blank page. So now we are going to solve question number 13b from section B. So 13b, here it was already stated that when the lights were on, the teacher has already said that the LDR, the resistance of the LDR was about 9 ohms. So the teacher has already said that the resistance of the LDR is 9 ohms, and even though now the current lights are on or off, it doesn't really matter the amount of current flowing through the circuit. So the current for LDR would still be the same, that was 2.38 into 10 to the power negative 4 ampere. And now we can use the equation V is equals to IR, and you just input the values, that is 9 into 2.38 into 10 to the power negative 4, and if you calculate it, you get a value of 0.002142 volt, which is almost like 0.002 volt. Now it was also stated in the last line of the question that the resolution of the voltmeter was 0.01, and as we can see that 0.002 volt is a lot less than 0.01 volt. So the value for the voltage of the LDR when the lights are on is less than the resolution of the voltmeter. So it is obviously not possible for the voltmeter to represent this voltage on its screen. So let me write the explanation. The value of the voltage for LDR is way too less, or is less than the resolution of the voltmeter, so the voltmeter cannot measure or determine the value for it. So the voltmeter cannot determine the value for it. So with this, our question number 13b ends. I hope question number 13b was clear. Question number 13b was clear, and now I'm moving to question number 14. Question number 14 says the diagram shows some of the energy levels of an atom of a hydrogen. So there are like 1, 2, 3, 4, 5 energy levels drawn in the question paper. Let me draw it. First energy level has a charge of 0 electric volt. Second energy level has a charge of negative 0.85 electric volt. And third one has an energy of 1.5 electric volt. Fourth one has an energy of 3.4 electric volt, and the last one has an energy of negative 13.6 electric volt. Now it says that when an electron with a kinetic energy of 12.3 electric volt interacts with this atom, an electron in the atom moves with the 13.6 electric volt level to the 51.5 electric volt. So here it says that an electrode was in its ground state, and when another electron strike it with an energy of 12.3 electric volt, this electron moves from this ground state to the second state, that is, it moves from the ground state to the second level. And when this exact electron was hit by a photon with energy 12.3 electric volt is incident, the electron in the atom doesn't change, or it just stays in the same position. When this same electron was heated by a photon molecule, this electron doesn't move from its ground state. Now we need to explain that why it moves from its ground state in case for the electron, but why it doesn't move from its ground state in case for the photon. So we need to explain this in words. Now for this, the explanation is that for photons, the energy must be specific, and for electrons, it doesn't have to be specific. It can absorb any amount of energy, and if it gets some energy in excess, the electron will put that energy for the leftover electrons. So let me write it down again. Here, when the electron was struck by another energy carrying electron, which actually provided an energy of 12.3 electric volt. I'm solving 14. Here the situation was that an electron of hydrogen atom was struck with another electron carrying kinetic energy. The energy that the electron provided to the hydrogen electron was 12.3 electric volt. And with this 12.3 electric volt, the hydrogen electron moved from the ground state to the second level. So the difference in energy, the amount of energy this electron used to move from the ground state to the second level is energy used by hydrogen electron is negative 1.5 minus 13.6, and if you calculate it, it is a value of 12.1 electric volt. But the electron was actually, the hydrogen electron was actually given 12.3 electric volt, which means that this hydrogen electron uses a 12.1 electric volt to move from the ground state to the second level, and the leftover energy, that is 12.3 minus 12.1, that is 0.2 electric volt, is left for the other electrons. So energy used, so this is the leftover energy, not energy used, this is the leftover energy. So for electrons, the hydrogen electron can actually accept a different fraction of electrons to move from the ground state to any level. But for photons, the energy must be 12.1 electric volt to move the electron from its ground state to its third or second level. The energy must be specific to this energy difference between the levels, and that's why for photon, the hydrogen electron doesn't move from its ground state. So let me write the entire explanation. When an electron, this is the answer part, that was still the explanation on the calculation. So this is the answer part. When an electron with 12 electric volt energy interacts with the hydrogen electron, with this hydrogen electron, the electron in this atom receives the electron in this atom receives receives 12.1 electric volt to move from 13.6 electric volt level to the negative 1.5 electric volt state, from the ground state to the state, and left the 0.2 electric volt energy for other incoming electrons. So when the atoms are heated by electrons carrying energy, the electrons inside the atom can receive energy from different combination. It doesn't have to be specific with the state difference. But when it is stuck with the photon, the energy of the photon must be specific with the difference between the levels. So that's why when this electron was heated by a photon carrying 12.3 electric volt of energy, the electron doesn't move from its ground state. So let me write it down. But when this electron was heated by a photon with 12.3 electric volt energy, the electron does not move from its ground state because the energy provided by the photon is not exactly the same, is not exactly equal to the energy difference between level. So with this, our question number 14 ends. This was the explanation for question number 14. I hope question number 14 was clear. Now moving to question number 15. Question number 15 says that a physics teacher placed a coin at the bottom of a cup. When viewing the cup from an angle, the coin was not visible, as shown in photograph 1. In photograph 1, there is just a cup with which we cannot see that it looks like that the cup is empty. Now, while still observing from the same angle, the teacher slowly poured water into the cup. The coin gradually became visible as shown in figure 2. The effect is caused by refraction. Explain what is meant by the term refraction. So they just need you to answer the term, that what is meant by the term refraction. So here we are going to solve question number 15 of section B. Now section B, in part A, it just wants you the explanation for a term, that is what is meant by the term refraction. Now refraction is a phenomenon when light passes from different medium, like from water to air or from air to water. Due to change in medium, their densities change, like air is less denser than water, so there is a density change in density, and due to change in density, the speed of the wave decreases, or the speed of the light changes also. And due to this change in speed, the entire direction of the light will get altered or just move towards the normal or away from the normal. So this phenomenon is in total called the refraction. So let's write it. When light moves between boundaries with different densities, their speed changes. When light moves between different boundaries, their speed changes. And due to this change in speed, there is a change in direction. There is a change in direction. change in direction. And with this, question number 15A ends. I'm moving to question number 15B. Here it says the simplified diagram below shows how a ray of light travels from the edge of the coin to the teacher's eye when the cup is partially filled with water. The diagram is not to scale, so here you need to, the question asks you to find the refractive index of the water in the cup. Now the diagram has a lot of labeled lengths and differences, so let me draw it a little. A base coin here, and there was a normal from this point approximately. And this is the water air change in boundary, and from there the teacher's eye was approximately on here. And the entire diagram is not to scale, so we need to find the angle of incidence and the angle of refraction. This length was given 1.8 centimeter, and this length was given 3.7 centimeter. This length was given 3 centimeter, and this length was given to be 4 centimeters. Yes, 4 centimeters, 4.0 centimeters. So we need to find the value for this angle and this angle. Value for this angle and this angle. So at first, this is the angle of incidence, and we need to find the value for angle of incidence. Now, angle of incidence actually makes a triangle with this entire structure. Let me draw it a little. The entire structure makes this triangle. This is the angle of incidence that we need to find. The base is 1.8 and the height is 3. So angle of incidence would be tan inverse 1.8 over 3.0, and if you calculate it, it gives a value of 30.96 degree. And then we need to find the value for the angle of refraction. Now refraction also makes a value or a triangle like this. If you draw the triangle for refraction, it looks like this, and this is the angle that you need to find. The value for this is 3.7 and this is 4. So angle of refraction is tan inverse 3.7 over 4, and if you calculate it, you get a value of 42.77 degree. And the value for the incidence, the value for the angle of the incidence, and the value for the angle of the refraction is now stated in the screen. And now we need to find the refractive index. Now there the light moves from two medium, from water to air. So here we need to find the refractive index of water and air boundary. So now I'm doing the rest of the calculation in this page. Now we were finding the value for the refractive index. The refractive index for there are two mediums, so it will be n1 n sine theta 1 is equals to n2 sine theta 2, and if you make the n1 subject, it will be 1. The n1 and 1 represents the water and air, so let me write it as water, air, and air. This refractive index in air, the value for refractive index of air is 1, so that would be 1 into sine of the value for the refraction. So here it will be 42.77 degree divided by sine 30.96 degree, and if you calculate it, you get a value of 1.32. So the refractive index for water is 1.32. I hope question number 15B is clear. Now I am moving to question number 16. Question number 16 is about two graphs. Of one graph is about filament and the other is about thermistor. Here the question says the graphs show how circuit how current varies with potential difference for a filament bulb and for a negative temperature coefficient temperature. Explain the shape of each graph. Your answer should include reference to the movement of conduction electrons in each component. So here you need to explain that why the graph for filament bulb and why the graph for thermistor looks like this. So let me first explain the reason for the filament bulb. In filament bulb, as the voltage increases, resistance also increases. So I'm explaining for filament bulb. Filament bulb. Now as the voltage increases, resistance also increases, because we know the equation V is equals to IR. V is equals to IR, voltage and resistance are directly proportional. So as voltage increases, resistance also increases. Now with increase in resistance, temperature will also increase. So increase in resistance increases the value for temperature. A rise in temperature means that the atoms are now vibrating more vigorously. So rise in temperature indicates that atoms start vibrating more vigorously. Now as atoms are vibrating more vigorously, it means that collisions will be more often. So it means more collisions between them, between the electrons. The electrons are colliding more often, so collisions, more collisions. More collision means the drift velocity increases, and according to the equation I is equals to NA VE, as velocity increases, as the collision increases, the drift velocity actually decreases. And now as velocity decreases, current also decreases, because I and drift velocity are directly proportional. So it means that an increase in voltage with time, the rate of increase of current decreases. So rate of increase in current decreases because of this. This was the explanation for the filament, and now we are doing the same kind of explanation for the thermistor. So for thermistor, again, as V is equals to IR, as V increases, R also increases according to the equation V is equals to IR. Now as R increases, temperature of the circuit will obviously increase. In thermistor, as the temperature increases, the thermistor starts giving or losing more electrons. So number of electrons increases. As number of electrons increases, it means that number of charge carrier will increase. Number of charge carrier increase. Number of charge carrier increases. As number of charge carrier increases, according to the equation I is equals to NA VE, as charge carrier increases, current also increases. And as current, this indicates that rate of increase in current increases when voltage increases for thermistor. So this was the two explanation for the filament bulb and for thermistor. I hope it was clear. Now I'm going to write the answer in the next page. The answer for question number 16, the answer section is here, and it is for filament bulbs. For filament bulbs, as voltage increases, resistance also increases. Resistance also increases. A high resistance increases the temperature. So here we can write it as, for filament bulb, as voltage increases, resistance also increases, which increases the temperature. A high temperature A high temperature causes the atoms to vibrate more vigorously, causes the atoms to vibrate more vigorously, causing an increase in the rate of collision, causing an increase in the rate of collisions. And according to the causing the an increase in the rate of collision between a collision which decreases the drift velocity. According to the equation, I is equals to NAVE, rate of increase of current also decreases. So this was the entire part for the filament bulb. Now I'm moving for the thermistor. So let me write it as for thermistor. For thermistor, resistance decreases as resistance increases as voltage increases. So resistance increases as voltage increases, which increases the temperature. A rise in temperature a rise in temperature increases the number of free electron, increases the number of free electrons, which therefore increases the number of charge carriers. And according to the equation, according to I is equals to NAVE, current increases. And with this our entire question number 16 ends. Let me zoom in. So this was the question number 16. I hope question number 16 was clear. I'm moving to question number 17. Question number 17 says ultraviolet light of wavelength 20 nanometer is incident onto a metal surface. The metal has a work function of 3.68 electric volt. Electrons are released by photoelectric effect. Part A, calculate the maximum speed of electrons as they are released from the metal surface. So we need to find the speed with which the electrons are leaving the metal surface. Now I'm solving the question number 17A for section B. 17A. At first, the certain things that are given in the equation is the wavelength and the speed. We all know the speed of light is actually 3.0 into 10 to the power 8. So the only information given in the equation is wavelength so far. So we can use the equation V is equals to F lambda, and we have to make F the subject, so it will be F by lambda, and that's 3 into 10 to the power 8 over 20 into 10 to the power negative 9. And if you calculate it, you get a value of 1.5 into 10 to the power 6. 1.5 into 10 to the power, let me calculate it. Wait. 3 into 10 to the power 8 over 20 into 10 to the power negative 9. And you get a value of 1.5 into 10 to the power 16 hertz. So this is the frequency for the ultraviolet light. And now the work function is also given. So according to this frequency and Planck's constant, we can find the energy, that is 6.63 into 10 to the power negative 34 into 1.5 into 10 to the power 16. And if you calculate it, you get a value of 6.63 into 10 to the power negative 34. You get a value of 9.945 into 10 to the power negative 18 joule. Now the value for the work function given in the question is, 3.68 electric volt. So that's why we need to convert it from electric volts to joules. So that's why we need to multiply with this value with 1.6 into 10 to the power negative 19. And if you calculate it, you get a value of 5.888 into 10 to the power negative 19 joules. And this is a value for the work function in joules. And now we can use the equation HF, that is the energy is equals to work function plus kinetic energy, that is half mv square, and we need to make the v the subject, so it will be HF energy minus work function over, and obviously it needs to be multiplied with 2 over the mass and root over. And you have to just put in the values. The value for energy was 9.945 into 10 to the power negative 18. Subtract the value for the work function, that was 5.888 into 10 to the power negative 19, and you need to further multiply it with 2 and divide by the mass of an electron, that is 9.11 into 10 to the power negative 31. And if you root over this entire value, you get a value of 4532163.384 meters per second. And if you write it in standard form, then it will be 532 into 10 to the power 6 meters per second. So this is the value for the velocity with which the electrons leave the metal surface. And with this, our question number 17 ends. I hope question number 17 is clear. 17A is clear. So now we're moving to 17B. Question number 17B. 17B says a student suggests that if the wavelength and intensity of the light used are both increased, the maximum speed of the electrons released from the metal surface also increases. Explain whether the student's suggestion is correct or not. So the student is saying that if you alter the intensity and the wavelength of the light, the electrons being released from the metal surface, the speed of the electrons being released from the metal surface will also get changed. So the wavelength actually matters, because the wavelength, if the wavelength increases or decreases, the speed of the electrons also increases or decreases. But the intensity doesn't affect the speed of the electrons moving from the metal surface in any way. So change in intensity doesn't have any effect on the speed of the electrons, but change in wavelength does have effects on the speed of the electrons. So let's write the answer. Increasing wavelength leads to more photon emission which leads to more electrons release, which leads to more electrons release, but it does not affect the speed of the electrons. But increasing the wavelength decreases the photon emission which results in decreasing the speed of electrons. So the student is correct. And with this, our question number 17b ends, and also the entire question number 17. I hope question number 17 was clear. Moving to question number 18. A teacher has a laser pointer. The laser pointer emits a narrow beam of plain polarized light. Describe how the teacher can demonstrate that the light from the laser pointer is plane polarized. So in question number 18a, it asks you that how can you determine that a certain light is plane polarized or not. We know that plane polarized light only vibrates in one certain plane. So if you pass the plane polarized light through a filter, polarized filter, then it will only travel through that certain filter. But if you rotate the filter, then the intensity of the light will start decreasing, and at a certain point the intensity of the light will be 0, indicating that the light was plane polarized. So let me write the entire process. We are now solving question number 18a of section B. Question 18a. Question 18a, we can write it as he can determine this by directing the light through a polarized filter, and he need to rotate the filter until no light can pass through it. And by this procedure, the teacher can determine that the light is polarized or not. So this was the end for question number 18a. I hope it was clear. Moving to question number 18b. 18b, it says that the teacher shines light from the laser pointer onto a diffraction grating as shown. The process is this produces a diffraction pattern on a screen, and then diagram is in the question paper. In part B1, it says that the diffraction grating is equals to n lambda is equals to d sine theta. State the quantity represented by d. Now d represents the slit spacing, the distance between the adjacent lines. So we can write it as here B1, d represents the distance between the adjacent slits. Now with this our B1 ends. Moving to B2. In B2 it says the teacher made the following measurements. Distance from central maximum to the first order maximum is 1.61 meter. Distance from diffraction grating to screen is 2.74 meter. And the wavelength of the light from the laser pointer was 532 nanometer. Calculate the lines of number of lines per millimeter on the diffraction grating. So we need to first draw the diagram for me to explain it to you in detail. I'm now solving the part B2 of question number 18. B2 of question number 18. Now the diagram was something like this. A straight line, and it was splitted into two. This was the screen. And this was the diffraction grating. This was the first order maxima, and this was the central maximum. Then this was the screen. Let me label it down. Screen central maximum. And this was the first order maximum. This was the diffraction grating. And this was the light from the laser. Now we need to find the first thing that we find is this theta, the value for this theta. The value for the distance from the diffraction grating to the screen, that is this value, is given 2.74 meter, and the value for the first order maxima from the central maximum was given 1.61 meter. So we can easily find the value for theta by using the tan. So value for theta would be tan inverse 1.61 over 2.74, and if you calculate it, you get a value of 30.44 degree. Now using the equation from that was given in the 18B1, that was n is equals to n lambda is equals to d sine theta. We need to make d the subject of the equation, and it will look like d is equals to n lambda over sine theta. The value for n here, it will be just 1 because the entire process is taking place in air. So it will be 1 into the value for lambda, that was 532 into 10 to the power negative 9, because we always take the value for wavelength into meters. So that's why we need to multiply it with negative 10 to the power negative 9 and divide it with the value of the sine theta. So it will be sine 30.44 degree. And if you calculate it, you get a value of 1.05 into 10 to the power negative 6 meter. So this was the value for D. Now the question wants you to find the value for the lines per milliliter. So let me do the other workings in here. The value for D is, actually the equation for D is 1 over lines per meter is 1.05 into 10 to the power negative 6. And now we need to find the value for the lines per meter first. Lines per meter, and that will be 1 over 1.05 into 10 to the power negative 6, which gives a value of 9.52 into 10 to the power 5. So this is the value for the lines per meter. And now we need to find the value for the lines per milliliter. Milliliter means that we need to divide it by 1000. So lines per millimeter is 9.52 into 10 to the power 5 over 1000, and you get a value of 952 millimeter. So part B2 is also given. We have calculated the number of lines per millimeter on the diffraction grating, and that is 952 millimeter. I hope question number B2 was clear. Moving to B3, Here it says using this diffraction grating and laser pointer, only the first order maxima and the second and the central maxima are produced. Explain how the teacher using the same laser pointer could improve this value for the number of lines per millimeter. So here that the thing that he can do to increase the percentage uncertainty, so decrease the percentage uncertainty and make the entire procedure more accurate, is by moving the by moving the diffraction grating away from the screen. So when he moves the diffraction grating away from the screen, it produces first order maxima on both sides of its central maximum. It produces first order maxima on both sides of the central maximum. And now he can calculate the distance from the central maximum to the first order maxima from both upper distance and lower distance. Let me draw a diagram for it. Like when you move the diffraction grating away from the screen, the entire thing looks like this was the main light laser, and it moved away, moved from the diffraction grating. In the previous situation, we saw that it produces just one first order maxima. Now as the distance between the screen and the diffraction grating has increased, it now produces a first order maxima for in here too. And now the teacher can measure the distance from the central maxima to the first order maxima. This is also the first order maxima, and this is also the first order maxima, this and this. So he can calculate the distance twice, and this would improve his value for the number of lines per millimeter, and thus decrease the value, thus decreases the percentage uncertainties. So I'm gonna write the value answer for part B3 in the next page. B3, the teacher should increase the distance of diffraction grating to screen as this produces first order maxima on both sides of central maximum he should then measure the distance from central maxima to the first, this was maximum, to the first order maxima for both sides it would decrease the percentage uncertainty. Percentage uncertainty. And with this our question number B3 ends. So this was the entire ending for B3. I hope B3 was clear, and with this our entire question number 18 ends. And now I'm moving to question number 19. Question number 19 says a student carried out an experiment to determine the resistivity of a nichrome wire. Her circuit included an ammeter, a voltmeter, and a variable resistor. Complete the diagram for this experiment. So in part 9a, nichrome wire is drawn. So we need to draw the other parts of the other parts of the circuit around this wire. So let me draw it. 19a, we need to have a power supply, obviously. And with this, the nichrome wire is connected, and there should be a variable resistor and an ammeter connected in series, and a voltmeter connected in parallel around the nichrome wire. So part A is done. Moving to part B, the student varied the length of the nichrome wire in the circuit. For each length, she measured the potential difference across the nichrome wire. She used the variable resistor to keep the current in the wire at 0.2 ampere during the experiment. The student plotted a graph of potential difference against length of nichrome wire. So I have actually plotted the graph for this. I'm just moving to that page. Okay, so this is the page, and now we are solving the part B2. Here it says they determine the resistivity of nichrome wire. The cross sectional area of nichrome wire is 5.31 into 10 to the power negative 8, and the resistivity, actually voltage over length, the gradient for this graph gives you the value for the resistivity. So gradient for this graph gives you the value for the resistivity. Resistivity is represented using R, capital letter R, and you can find it by, you can see that it actually ends on 4.1. Yes, it approximately ends on 4.1 here on graph, and 1 meter length. So the gradient will be 4.15 actually. It's somewhere between 4.1 and 4.2. So 4.15 over 1 will obviously give you the value for the resistivity as 4.15. Now you can use the equation for the resistivity. That was resistivity is equals to, so resistance is equals to resistivity into current, into current over area, cross-sectional area. Now you have to find the resistivity, so make resistivity the subject, and the equation will be like resistance into area over current. And area was already given in the question, that was 5.31 into 10 to the power negative 8. So it is 4.15 into 5.31 into 10 to the power negative 8 over current. The value for current, was 0.2 ampere. It was given at the top of the question B. So it was 0.2, and if you calculate it, you get a value of 1.101.825 into 10 to the power negative 6 nanometer. And you can obviously write it as 1.10 into 10 to the power negative 6 ohms meter, not nanometer, ohms meter. And with this, our 19B1 ends. So moving to 19B2. 19B2 says calculate the power dissipated from the nichrome wire to the surroundings when the length of the wire is 0.75 meter. So when the length of the wire is 0.75 meter, approximately in here, we can see that it gives actually a value of 3.1. When the length of the wire is 0.75 meter, the voltage is 3.1 volt. So using the equation, So now we are going to solve B2 using the equation power is equals to VI. The voltage is 3.1 and the current is 0.2, so it gives a value of 0.62 watt. When the length of the wire is 0.75 meter, the value for the power is 0.62 watt. And this was the value for working for question B1. And with this, our question number 19 ends. Moving to question number 20. So now we are going to solve question number 20. Question number 20 says that a smart meter collects information about the use of electricity in the home. This information is transmitted to the electricity company using radio waves. A typical smart meter emits radio waves with a power output of 1 watt and intensity of radiation greater than 4.5 watt per meter square is dangerous to people. A person stands to 25 centimeter from a smart meter. Deduce whether the radiation emitted by this smart meter would be dangerous to the person at this distance. So we know that the radiations are actually transferred in two ways, perpendicularly or radially. And here, as the question doesn't use the word perpendicular, that means the radiations are getting transferred in radial way. And radial way means that the distance of the person from the smart meter is actually the radius. So the radius for the radial transmission is 20A. The radius is 25 centimeter. So we need to convert it to meters. So that's why we need to multiply it with 10 to the power negative 2, and it gives you a value of 0.25 meter. And now we need to find the intensity for this part. Intensity, we can find it by using the equation intensity into power over area. The power in this, the specific smart meter has a power of 1 watt, so the power is 1, and the area is 4 pi r square. Pi was 0.25 square, and if you calculate it, you get a value of 1.27 watt per meter square. And we can see that as 1.27 watt per meter square is less than 4.5 watt per meter square. So the radiation is not harmful for the person at this distance. So the radiation is not dangerous to the person at this distance. And with this, question number 20 ends. I hope question number 20 was clear. Moving to question number 20b, it is suggested that the energy per photon could be important in determining if the radiation emitted by the smart meter is dangerous. The smart meter transmits radio waves of frequency 902 MHz. Calculate the energy per photon in electric volts of the photons emitted by the smart meter. So we need to find the value for the energy basically in electron volt, energy per photon in electron volt. So we can find it by using the equation E is equals to HF divided by the charge of an electron. That is divided by charge of an electron is 1.6 into 10 to the power negative 19. And if you put the values in, the value for H, Planck's constant, is always constant. So it is 6.6, 3 into 10 to the power negative 34 into the frequency is 902 megahertz. That means 902 into 10 to the power 6 over 1.6 into 10 to the power negative 19. And if you calculate the entire thing, you get a value of 3.74 into 10 to the power negative 6 electron volt. So the value for the energy per photon in EV is 3.74 into 10 to the power negative 6 electric volt. And with this, our question number 20B ends. I hope question number 20B is clear. Moving to question number C, 20C. Question 20C of section B. The display of the smart meter is in one household is shown. This shows the total electrical energy used in one day. 1 kilowatt H is a unit of energy equivalent to 1 kilowatt of power used for 1 hour. The kettle in this house has a power of 1200 watt. The kettle takes 125 seconds to heat the water. The kettle then switches off. The student suggests that boiling the kettle once uses less than 1% of the total energy shown on the smart meter display. Assess the student's suggestions. So first, let us find out the energy used by the kettle in boiling the water. So energy used by kettle, and that is the power into time. It gives you a value of 5.98 into 10 to the power negative 25 joule. And then we need to find the energy of the entire house, energy used by the entire house, and that is 6 into 8, 5, the reading shown in the diagram for 20C. 6 into 8, 5 into 10 to the power 3, 10 to the power 3, because it was said 6.85 kilowatt. Kilo stands for 10 to the power 3. So that's why we're multiplying 10 to the power 3 into 3600, and it gives you a value of 24660000 joule. I made a mistake. If you calculate 1200 and this, you get a value of 15000 joule. This is the value for the energy used by kettle, and this is the value for the energy used by the entire house. And now we need to find the percentage efficiency. And that will be power used by the energy used by the kettle, that is 15000 over energy used by the entire house, 24660000 into 100%, and you get a value of 0.61%. And we can see that 0.6% is less than 1%, so the student is correct, as 0.61% is less than 1%, so the student is correct. And with this, our question number 20C ends, and our entire paper for January 2021 Physics Unit 2 IAL also ends. I hope all my explanation was clear enough, and the link for the official paper will be uploaded in the description box. The link for the official mark scheme will also be uploaded in the description box. And this was the end for the entire paper. I hope it was clear and helpful. If you want me to do any solution for certain paper, you can comment it in the comment section. And if you have any problem in this paper that I just solved in this video, you can also comment it in the comment section. I am really waiting for your comments. Thank you for watching.